Witamy na drugiej części warsztatów Przez sztukę do nauki. Za chwilę uczestniczyć Państwo będą w niezwykłym wykładzie Geometria muzyki. Matematyczne meandry muzyki, tajemnicza liczba pi i inne. Geometria muzyki to wynik współdziałania naukowców z Wydziału Matematyki i Informatyki UAM i artystów z Poznańskiej Akademii Muzycznej. Muzycy i matematycy próbują znaleźć odpowiedzi na nurtujące ich pytania dotyczące wzajemnych relacji pomiędzy sztuką i nauką. Czy matematykę można usłyszeć w utworze muzycznym? Czy matematyczne ciągi mogą być inspiracją do napisania utworu muzycznego? Czy w dziele muzycznym można odnaleźć przekształcenia geometryczne? Odpowiedzi na te pytania nie są proste. Prezentowane w ramach wykładu utwory, opatrzone stosownym komentarzem, są wynikiem poszukiwań odpowiedzi i wprowadzają słuchacza w mało znane przestrzenie na granicy nauki i sztuki. Welcome to the second part of the workshop Through Art to Science. In a moment, you will participate in an unusual lecture, The Geometry of Music. Mathematical meanders of music, the mysterious number pi and others. Geometry of music. It is a result of cooperation between scientists from the Faculty of Mathematics and Computer Science of Adam Mickiewicz University and artists from Poznań Academy of Music. Musicians and mathematicians try to find answers to questions concerning mutual relations between art and science. Can mathematics be heard in a piece of music? Can mathematical sequences inspire to write a musical piece? Can geometric transformations be found in a work of music? The answers to these questions are not simple. The works presented during the lecture, accompanied by appropriate commentary, are the result of this search for answers and will introduce the listener into little-known areas bordering science and art. A teraz chciałbym przedstawić wykonawców wykładu Geometria muzyki. Całość poprowadzą w roli profesora Maciej Grześkowiak z UAM, w roli matematyki Karol Gierszewski, również z UAM, oraz w roli muzyki Monika Kędziora z Akademii Muzycznej w Poznaniu. Ilustracje muzyczne realizować będzie zespół muzyków Piotr Niewiedział przy fortepianie, Paweł Kroczek na klarnecie i Piotr Sołkowicz na wibrafonie oraz zespół rytmiki Akademii Muzycznej w Poznaniu przygotowany przez Kingę Cejnową i Agnieszkę Chęczkę-Orłowską. And now I would like to introduce the performance of the Geometry of Music lecture. The whole lecture will be conducted by Maciej Grześkowiak from AMU as the professor, Karol Gierszewski also from AMU as mathematics, Monika Kędziora from the Academy of Music in Poznań as music. Musical illustrations will be provided by a team of musicians, Piotr Niewiedział at the piano, Paweł Kroczek on the clarinet, and Piotr Sołkowicz on vibraphone, and by the rhythmics ensemble of the Poznań Academy of Music prepared by Kinga Cejnowa and Agnieszka Chęczkę-Orłowska. Zapraszamy na wykład. Please enjoy the lecture.
I would like to begin our lecture with the following question. What are the elementary objects in music and geometry?
I think that in geometry an elementary piece is a point. The point is represented by a dot. It is named with a capital letter. The point is an exact location or position you can see on this picture. A point has no dimension, that is, no length or width.
What is the fundamental particle in music?
The fundamental particle in music is a sound, but unlike in geometry, the sound has few basic parameters like pitch, like length and volume. So we have many different sounds.
Can sound be presented or danced?
Yes, we can play few examples of the sound like that.
But can we see that sounds?
Yes, of course, we have some special signs for sounds, and we call them just notes.
And that is all?
No, we need some more, let's say, some tools to give musicians more informations. And to give an exact name to the note, we need a special system of 5 lines, and we also need a key for opening this 5-line system.
Like that?
Yes, exactly. And now we can put, for example, like here, 12 notes, and we can make chromatic scale.
What is the difference between a point and a sound? Can't we draw it in somehow?
Yes, we can draw the time axis and name it t. This axis will refer to the duration of the sound. Next, we draw the pitch axis and name it p. This axis will refer to the pitch. How do we number the axis? We write 1, 2, 3, 4, and so on the time axis, and C, C sharp, D, D sharp on the pitch axis. Now we mark sound C in our coordinate system. Look at what we have drawn here. We can see that it has 2 endpoints. These 2 points mark the beginning and the end of the sound duration. This is called a line segment.
So we can interpret the sound as a source segments. Can any system of segments represent a melody? For example, one like this. In addition, we will mark by a dot the beginning of such sounds.
In this way, we got segments of different length which correspond to a different duration of sounds. Is it possible to write sounds in this way in music?
Well, when we look at this example, in fact, we can see the same time values of the notes apart of the last few, because there are some repetitions of sounds on the same length. But yes, it is possible to write music in this way. But first, let's start from the very beginning. Every performer, every musician has to know a special binary tree with branches, divided sounds lengths from very long to very short. So we can divide, like here, whole note into 2 half notes, and so on, till the shortest. Here we have 30 seconds notes. And now we can show our melody you wrote with rhythmical values.
And what is that?
Just look and listen to it.
Karol, in geometry we sometimes involve moving shapes on a plane. Can you tell us something about it?
The translation is one of three basic transformations that can be done to a figure. The translation moves the object like this. What exactly does this mean? Every point of the shape must move the same distance in the same direction. We have two components of this movement, horizontal and vertical. Each point of the triangle is shifted by 5 units to the right along the horizontal axis. Next, each point of the triangle is moved by 2 units up along the vertical axis. That is a basics of translation.
Can music be shifted?
Yes, of course. And we have some special situations for such transformations, and we call it polyphony, which means a musical piece made with 2 or more independent voices. And here we have such example, which belongs to the last work written by Johann Sebastian Bach. I would like to explain that we use Bach music here because his musical genius is such important for music, like, for example, Isaac Newton for mathematics or physics. And that composition of the title, The Art of Fugue, is like the book about such wonderful geometrical transformations we can do in music. And the first example is the first translation of the basic figure we can find in polyphony called just theme. This is that melody written in first 4 bars. That theme, like a geometrical figure, is moved from one voice to the other. But first we can see it and listen it, so the basic version of theme.
Can we express translation of music in the language of geometry?
Yes, we can draw it and thus show it. To show this, we will work with just a portion of the musical theme. Let's color it in red, like this. Next, let's map the musical theme in the Cartesian coordinate system in the same way as we did before. In this way, we get a geometric object corresponding to the music. Now, let's move the shape without changing its size on the plane. All we need to do now is map the blue shape to the musical notation to see how translation works in the math and music.
Okay, I would like you to ask to listen to first part of the Art of Fugue, that is contrapunctus number 1. While musicians will play that 4 voices fugue, you can follow the translation of the theme from one voice to the other, and you can see it with help of choreography. So remember, every 2 dancers mean one different voice, and we can also follow theme in the voices in our ensemble. 2 of them are in 2 hands of our pianists. One is in the clarinet part and one in vibraphone.
Carol, you mentioned that in geometry, 3 basic transformations can be performed on figures. One of them you have already mentioned, it was translation. When is the next one?
The next geometric operation is an axial symmetry or a reflection. When reflecting anything across the horizontal axis, there is a simple rule that we can follow. That is, reflecting across the horizontal axis, the original x-coordinate of your coordinates stay the same, and your y-coordinate changes. Let's demonstrate the rule of the reflection with one example. We see that the value of time coordinate will not change during this reflection. However, we see that the value of the pitch coordinate will change.
Monica, it is possible to do symmetrical reflections in music. Can you tell us something about it?
Yes, symmetrical reflection in music are known and very popular since Renaissance style. But I will present it on the same example. I will just call another fugue from The Art of Fugue by Johann Sebastian Bach. Remember, even we can listen to the next piece, we can notice that Bach uses the same theme, the same melodical and rhythmical figure. And now, when we look at the score, we, in fact, can see 2 different melodies. That is why, because we took the first note of the mirror as a mirror and just make a symmetrical reflection. And we, in music, we call such process as inversion. We can listen to it and we can see it, of course. First, we will see the original version, the basic theme, and then we can follow inversion.
Carol, can we visualize this process geometrically?
Yes. Geometrically, it corresponds to a specific axial symmetry. We choose axis. In this example, the horizontal line at the height corresponding to the point in the middle between F sound and F sharp sound. Then we reflect with respect to this line our geometric representation, colored red, of the theme we have just seen and heard. In this way we obtain the blue-colored inverted theme.
But the reflections is not perfect.
Yes, correct. You can see that there are red intervals lying off the axis of symmetry which were not moved. In the standard axial symmetry, only points lying on the axis are fixed. Here we can see some deviations. This is the place where music needs to dominate pure geometry in order to preserve harmony.
Can we reflect music symmetrically to the vertical axis?
Well, in mathematics you can compare and move objects on the surface, and in music you cannot make such observations because musical objects are developing in time. And sometimes it is also very difficult to hear these objects because of its complexity. But yes, such elaborate polyphony we can find in Renaissance and Baroque music, and obviously in the Art of Fugue by Johann Sebastian Bach. There are a few very special fugues where every piece has two parts named rectus and inversus, and these parts are the exact mirror of themselves. So rectus starts with theme going up from the lowest voice to the highest one, and inversus is like a reverse of the same theme, but inverted, goes down from the highest voice to the lowest voice. And such complex polyphony we call the mirror fugue. But from the other hand, it is also kind of inversion, but in larger scale.
What rules are used in mathematics when a figure is reflected in respect to a vertical axis?
When reflecting anything across the vertical axis, there is a simple rule that we can follow. That is, reflecting across this vertical axis, the original pitch coordinate of your coordinates stay the same, and your time coordinate changes. Let's demonstrate the rule of reflection with the example. We see that the value of pitch coordinate will not change during this reflection. However, we see that the value of time coordinate will change.
Shall we follow the reflection in music, Monika?
Well, as I said before, it is not so easy to catch that reflection because both parts, rectus and inversus, cannot be played simultaneously. But I suppose the best illustration of that special geometrical situation is just music. So let me ask our artist to play and show us the reflection, first rectus and second inversus.
Karol, have you encountered shapes that are created by shrink certain figures? These figures might be horizontally or vertically shrink. In this way, we obtain a new shape which has different width and height.
Yes, we can find transformation of this type in geometry. One of them is shrinking figure along the x-axis or time axis. To be more precise, horizontal shrinking happens when shape is narrowed along the x-axis towards the y-axis, or time axis, or pitch axis, exactly like in the slides. This triangle will be shrunk in the direction that the green arrow points. Along the x-axis, the entire area of the triangle will be shrunk except for the points lying on the vertical dashed line containing the side of the triangle that is parallel to the pitch axis. In this way, we have a new triangle.
Are this kind of transformations possible in music?
Yes, in fact, we have the same transformations, but we use different names. And for example, shrinking in music we call as diminution. That relates to rhythmical shape of melody and means that we can decrease time values of the notes only. And finally, we have, like here, the melody with notes half the original value, like cutting for smaller pieces.
Karol, you have mentioned that in geometry we can shrink figures. Can we also make them stretch?
Yes, we can easily do it. Let's look at the slides to see it. Horizontal stretching happens when a shape is widened along the x-axis and away from the y-axis. The triangle will be stretched in the direction that the green arrow points, so along the x-axis. The entire area of the triangle will be stretched, except for the points lying on the vertical dashed line containing the side of the triangle that is parallel to the y-axis. In this way, we have a new triangle.
What about the music? Can we stretch notes?
According to diminution, there is opposite process also called augmentation, when one can increase time values of the notes. And for example, like here, instead of half notes, we have the whole note, and we can increase and so on and so on. And usually composers combine the direct and contrary motion of the theme. We have just seen that as translation and inversion with augmentation and diminution, and put everything into, let's say, 4 voices fugue. And such construction we can hear in the next musical example. It is just a fragment of Contrapunctus number 7 from the same amazing piece written by Bach, The Art of Fugue. So please listen to the music and look at the 4 voices with these 4 different shapes of the main melody: the basic figure, inversion, diminution, and augmentation, and obviously translation.
Have we mentioned all the possible transformations that we meet in music?
Not exactly. There is one more special construction with the strictest imitation, and it is called canon. By the way, the word canon means the rule. There are canons written in inversion, of course, in diminution or augmentation, but also we can find the special shape in retrograde motion. canon concrescence. It is type of canon in which the imitating voice gives out the melody backward, because canon concrescence means crep canon.
How mathematics can explain it?
Such a canon can be modeled by a Möbius strip. It is a shape discovered independently by August Ferdinand Möbius and named after him, and by Johann Benedict Listing, and they both discovered it in 1858. One can obtain this figure by taking an ordinary rectangular shaped strip, rotating precisely one shorter edge by 180 degrees, and gluing shorter edges together as shown. It has a very interesting property. It has only one side. We'll just show it.
We'll see it with help of that car going on the surface. Okay, yes, such example we can find in another amazing piece composed by Bach. It is musical offering with phenomenal examples of geometrical transformations in polyphonic constructions. Well, that is really difficult to imagine it, so the best idea is to look at the score and to listen to it.
Let us see a film created by Jos Lees.
Yes, and now I would like to present you that wonderful piece. It will be last example of our lecture. Canon concretions for musicians and Möbius strip for mathematicians. And remember that one can find here both mathematical and musical beauty.